In this section, we will be taking a look at how to perform operations upon functions and something called composition of functions. Key concept box, operations on functions. Let f and g be any two functions. A new function h can be defined by performing any of the four basic operations on f and g. For example, we could do addition. H of x could be defined as the sum of f of x and g of x. So if they're giving us this example where f of x is 5x and g of x is x plus 2, then h of x would equal the sum of those two functions, so 5x plus the x plus 2. So h of x would equal 6x plus 2. The domain here would be all real numbers because it's linear. You can take any number, multiply by 6, and add 2. We could also do subtraction. So h of x could be defined as f of x minus g of x. So using our example, h of x then would be 5x minus the x plus 2. So we'd have to do 5x minus x minus 2, which would be 4x minus 2. And again, the domain would be all real numbers because that's still linear. You can take any number, multiply by 4, and subtract 2. We could also do multiplication. So h of x could equal f of x times g of x. So for our example, h of x will equal 5x times x plus 2. If we use the distributive property, we'll get 5x squared plus 10x. This is now quadratic, but if we think about it, our domain is still all real numbers because I can take any number, square it, multiply by 5, take that same number, multiply by 10, and then add those things together. Division is where we start to have to modify our domain because we can never divide by 0. So let's say h of x is equal to f of x divided by g of x. Then h of x will equal 5x divided by x plus 2. And now we have to start to modify our domain. In this case, our domain could be everything but negative 2. So x cannot equal negative 2, because if x were negative 2, I'd have negative 2 plus 2, which would be 0, and I'd be dividing by 0, which is impossible. So any number besides the negative 2 would work. And that's what the final sentence in the key concept box is referring to. The domain of h consists of the x values that are in the domains of both f and g. Additionally, the domain of the quotient does not include x values for which g of x equals 0. Because if we're dividing by it, it can't be 0. Let's define a new type of function, a power function. Has the form y equals a x to the b power, where a is a real number and b is a rational number. So let f of x equal the power function for x to the 1/2, and g of x equal negative 9x to the 1/2. So these can't be polynomials because their exponents aren't whole values. So these are power functions. We're going to practice using them to add and subtract. So if we add these functions together, f of x plus g of x will equal 4x to the 1/2 plus negative 9x to the 1/2. Well, we have the same variable with the same exponents, so we can combine like terms. 4 take away 9 is negative 5x to the 1/2. We don't like to leave fractional exponents. Remember that 1/2 really means the square root. So we have negative 5 times the square root of x. We could do the same idea with subtraction. So f of x minus g of x would equal 4x to the 1/2 minus negative negative 9x to the 1/2. Well, minus and minus really means to add, so I have 4x to the 1/2 plus 9x to the 1/2. So we get 13x to the 1/2. Again, we should write that in radical form to be formal. So we have 13 square root of x. So question 3 asks us to consider what are the domains of f plus g and f minus g. Well, the domain for f plus g we've got a square root, and if we're sticking with the real numbers, we can't square root a negative, so therefore x would have to be greater than or equal to 0. So we could say bracket 0 to infinity. And the same would actually hold true for f minus g, because again, we have a square root here. So that's the domain for both of those functions. The issue is this square root and the fact that we can't square root a negative if we want to get a real answer. So when is this positive? Well, it's positive when x is greater than or equal to 0. So from 0 to infinity would be fine for the x values. Two new functions, this time f of x equals 6x and g of x equals x to the 3/4. Now we're going to take a look at multiplication and division. So for multiplication, if we do f of x times g of x, we're going to get 6x times x to the 3/4. Well, remember when there's not an exponent written, it's a 1, but I can think of that 1 as 4 over 4, because I know when I multiply the same base, I need to add their exponents, and with fractions, I need a common denominator. So 1 whole is equal to 4/4. I'm going to add on my 3/4. So I'm going to have 6x to the 7/4. And that's the same as x to the 1 3/4 if you did it with mixed numbers, so that you can see for radical form, you've got an x to the first on the outside, and then you've got the 4th root of x to the 3rd power. Because we couldn't have x to the 7th under a 4th root, so we wouldn't be able to leave it like this in radical form. We got to take out a 4th power, and we'd be left with 3 extras. So this is your formal way of writing your answer in radical form. On to division. So if we take f of x and divide by g of x, I have to subtract my exponent when I divide the same base. So remember, this is a 1. We're going to think of that as 4/4, so that we have a common denominator in order to subtract. So 6 divided by the unwritten 1 here gives me 6. X to the first divided by x to the 3/4, I subtract, so I take 4/4 minus 3/4, I get positive 1/4. So I have 6, and then 1/4 means the 4th root of x. So then for the domains, both of these functions have a 4th root. But let's start with the product. So for the product, so the domain of f times g, well, the domain of this function would be everything because it's linear. This one, though, we've got a 4th root, and anytime we have an even root, if we want a real answer, we have to have positive values under here. So we would need x to remain positive at all times. So the domain x has to be greater than or equal to 0, or from 0 to infinity, because of that fourth root. A fourth root is like a square root. We can't have negative numbers in here if we want to get a real actual answer. Now the domain for the quotient, we have to be careful. We can never divide by 0. So we have to consider the fact that we're dividing by function g, and think about when this would be 0. We have to take that out of the mix. So x cannot be 0, because that would make your denominator 0. So we know that, first of all. X can't be 0. And then we also consider the fact that it's a fourth root. And if we want an answer, it'd have to be positive. So x would have to be greater than 0. We could use values beyond 0, so that's why we use a parenthesis this time instead of a bracket. This bracket means 0 works. We can equal 0. I can't equal 0 here. I have to be bigger than it because of the dividing issue. So I can use any values larger than 0. So that's addition, subtraction, multiplication, and division, and a review of how to find their domains, another application of domain. Now let's take a look at another new concept. So the composition of functions. The composition of a function g with a function f is h of x equals g of f of x. So rather than adding or subtracting or multiplying or dividing, we're going to use one function as the input of another function. So we're going to substitute it inside of the function in place of the independent variable, the x. The domain of h is the set of all x values such that x is in the domain of f and f of x is in the domain of g. So we're going to take function f, put it inside of g as the input in g, and then we're going to find our final output. Let's take a look at some examples. Okay, so when we are finding composition with an actual numeric value, so we're evaluating for an actual number, in this case 3, we can do it in a two-step process. So we can start here on the inside and find f of 3, which means to take function f, replace the x with 3, and then solve for your answer. So f of 3, 2 times 3, take away 7. So 6 take away 7 gives you -1. So they want g of f of 3. Well, f of 3 was just found to be -1. So I'm going to plug that here in place of f of 3. So I've got g of -1. So now I'm using my g function, I'm replacing x with -1. So our final answer, g of f of 3 equals +5. Now, when you're doing a composition of functions with the actual function, so rather than evaluating for a specific value, we can't break it up. We have to take the whole expression and substitute it into the other function. So here where it says f of g of x, well, f of g of x means that in my f function, I'm going to replace the input, the x, with g of x. So I'm going to take this function. When I get to my input, I'm not going to write it. I'm just going to put some parentheses, leave a blank space so I can substitute for my input. The input they want me to use is g of x. So I'm going to put the g of x function right in here. So f of g of x. Well, g of x is 5x minus 2. So I'm going to take this and put it in place of the x in the f function. So I'll get 4 times the quantity 5x minus 2 to the -1st power. So I've taken my g of x function and I've plugged it, I've substituted into f of x in place of the x. I kept everything else about f the same, 4 times this quantity, which is now 5x minus 2 to the negative first power. And now I just simplify. So f of g of x, well, anything to the negative first power tells me to take the reciprocal, so I've got to send it to the denominator. This is to the positive first power, so it's going to stay in the top. So it's 4 over 5x minus 2. Number 9 says to do the opposite. This time we're going to take function g and replace its input with the f of x function. So function g says 5 times some input, take away 2. So I leave my input space blank. They're telling me to put the f of x function in there. So I'm going to put f of x right here. And the f of x function is 4x to the negative first. So I'm going to take this and put it right here in place of the x. So g of f of x is equal to 5 times the quantity 4x to the negative first, take away 2. I keep everything about this function the same. It's 5 times the input. The input is now 4x to the negative first, and then I subtract 2. So 5 times my input, which is the 4x to the negative first, take away 2. And now I simplify. So g of f of x will equal 20 x to the negative first, take away 2. Again, I can't leave a negative exponent. It means to take the reciprocal. Remember that only the x is to the negative first. The 20 is to the first power. So the 20 will stay on top, the x will drop to the denominator, and then the minus 2 stays up top. So it'll be 20 over x, take away 2. You can also compose a function with itself. So f of x means I'm going to take function f, which is 4 times some input to the negative first power, and that input that they want me to use is the entire f of x function. So it's going to go in here. So f of x means that I'm going to have my 4 times some input to the negative first, and that input I want to use is actually the f of x function. So I'm going to put 4x to the negative first inside of there as my input, so that I've literally substituted the f of x function into the f of x function in place of x. And now I simplify. So I need to distribute this exponent to the 4 and to the x to the negative first. I keep my 4 that's on the outside outside, so I have 4 times 4 to the negative first times x to the positive first, because when I have power of a power, you multiply. So this was 4 to the first, 1 times negative 1 gives you negative 1. This was x to the negative first, negative 1 times negative 1 gives you positive 1. So I need to get rid of that negative exponent. So we've got 4 times the quantity. The x has a positive exponent, he stays in the top. The 4 had the negative exponent, so he goes to the bottom. And now I have to multiply those two to help me take the whole number times the fraction. I'm going to remind myself that the whole number is over 1. So f of x is 4x over 4. But that's really just x. And so what we've just shown is that when you compose f with itself, so f of x, all of the other operations cancel out and lead you back to your original input of x. This is actually proving that this function is its own inverse, which is something we'll talk about in the next lesson, and we'll start to really apply composition of functions.